Welcome back. Today I'll be showing how to use various sensors with a Raspberry Pi in Python, including an ultrasonic distance sensor and an IMU, which stands for Inertial Measurement Unit, and these are useful for anything that involves motion, including navigation applications, and are an essential part of any aircraft and other vehicles. They're also useful for many robotics and home automation projects, which are the sorts of things I plan to focus on in future videos. Now, this video is actually a continuation of a few others I've done on the Raspberry Pi's GPIO pins. So if you haven't seen those, then check out my Raspberry Pi playlist after watching this one. Also, if you enjoyed these detailed guides, then be sure to give the video a thumbs up and also subscribe to the channel if you haven't already. This is the easiest way to help the channel out, so thanks in advance. Now let's get started and head over to the written guide on my website, which has been updated to include today's examples. You can find the link to it in the video description. The first half of the guide was covered in previous videos, so let's scroll down to the distance sensor example. I also included Amazon links for both of the sensors I'll be using today. Let's start with the ultrasonic distance sensor, which is only $7 for a 2-pack. And although this is a budget sensor, it's surprisingly useful for many applications. Unlike many other sensors which use either I2C or SPI for communications, this one just uses a simple digital input and output pin to communicate with an SBC or microcontroller. This means that we could use the RPi LGPIO library that was used in the previous video, but this would require us to read through the datasheet for the sensor and create our own functions to interface with it properly. This is probably still a good exercise to do if you really want to gain more experience and understand how to interface with sensors. Also, if you wanted to use this sensor with a microcontroller, then you wouldn't have a choice but to write out all the code yourself. Or you could search for it online and adapt it to your particular microcontroller's I/O configurations. But since we're using the Raspberry Pi, the libraries are already available, which makes everything super easy for us. So today we'll be using an alternative beginner-friendly library called gpiozero, which can replace the previous libraries we used in the previous videos. For example, instead of assigning pins as generic input or outputs, you can directly assign each pin as an LED, push button, and several more devices, including the distance sensor we'll be using today. For things like LEDs and buttons, it's not that much different than the previous library, but for things such as the distance sensor, it does make things quite a bit easier. All the functions are already written for us, so all we need to do is call the appropriate function and it will return the measured distance. If you want to see more examples using this library, I left a link to this article here, so I suggest checking that out after watching this video. Now, installing gpiozero is super easy, and it's actually already pre-installed on the official Raspberry Pi OS, but if you're using Diet Pi, you can install it with this command here. Alternatively, you can also install it with pip if you prefer, which might be necessary if you're using a different SBC other than the Raspberry Pi. Also, this library won't conflict with the other libraries I previously used, so you can keep both installed and choose the one you want to use by importing it in your Python program. Now, when it comes to connecting this sensor to the Pi, it's pretty straightforward, except you'll need to set up a voltage divider on one of the pins. When you call the function to measure the distance, the Pi will send a high signal on its output pin, which in this case I have set to pin 7. But you can set this to any GPIO pin you want. This pin is connected to the sensor's trigger pin, which tells it to start measuring. After the Pi sends this signal, it will start a timer and wait for a response in its input pin, which in my case I've assigned to pin 11. This is connected to the sensor's echo pin. Since this sensor runs off 5 volts, it will output a 5 volt signal here. But like I explained in the previous video, the Pi's pins are only rated for 3.3 volts, so we need to set up a voltage divider. I decided to use smaller resistor values in this example compared to the previous video's push button example, just to show that the exact resistor values don't matter. It's the ratio between the two resistors that's important. As long as you stay in between around 100 ohms and 100K for each resistor and keep the same ratio between them, the voltage divider should work fine. So now let's run the code. I've already logged into my Pi with an SFTP connection so that I can create and modify files from my desktop PC. So I'll create a new file and name it distance.py, then I'll copy and paste the example code here. Now you'll want to assign the appropriate input and output pins you want to use with this function here. Keep in mind the numbering scheme for this library follows the GPIO numbering, not the pin numbering. So you'll want to use these numbers instead of the numbers in the middle. Now the main loop is extremely simple. All it's doing is measuring the distance once every second and printing it to the terminal. So let's go ahead and run it. And as you can see, it's printing the values once every second as expected, and the unit of this value is measured in meters. When I move the sensor close to the table, we see the value below 0.1 meters, and when I move the sensor away from the table, we see values as high as 0.3 meters, which is roughly 1 foot. So these values make perfect sense. Let's now modify the code so we can make the LED respond to the sensor. Since we're using the gpiozero library, we can simply use its LED function to control the LED. So I'll copy and paste this line to import the function, then set my LED to GPIO pin 14. Now let's create an if statement. If the distance is measured to be less than 0.1 meter, turn the LED on. If not, then turn the LED off. Also, let's reduce the sleep time from 1 second to half a second, which will give us a faster reaction time. You could set this lower if you want, but unless your application actually needs to react faster, it's best to set this to a more sensible value. Now let's run the program, and I'll slowly move the sensor closer to the table, and the LED turned on just as expected. And when I move the sensor away from the table, the LED turns off. Now if I keep the sensor close to the table, the LED will remain on until I move it away and the LED turns off. Now before we move on to the next example, I also wanted to point out there's another low-cost distance sensor available on Amazon, but this one works using a laser instead of an ultrasonic wave, and it communicates over the I2C bus. The advantages of this one is that it's smaller and it works better when detecting objects at an angle. The ultrasonic sensor has a hard time with objects that are at an angle greater than 30 degrees. The ultrasonic sensor also has a longer range, so both of these sensors have their pros and cons. But anyway, I just wanted to point out that there are a number of options available when it comes to budget distance sensors. But now let's move on to the IMU, which again stands for Inertial Measurement Unit. These contain an accelerometer which measures the force or acceleration on the X, Y, and Z axis, and it also contains a gyroscope, which measures the angular rate, or in other words, the rotation speed along the X, Y, and Z axis. Some IMUs also contain a magnetometer to measure the magnetic field and to determine where north is. However, the IMU we'll be using today doesn't contain one of these. This is a budget IMU based on the MPU-6050, and you can grab a 3-pack on Amazon for only $10. The link is in the video description. Like I mentioned at the beginning, IMUs are useful for anything that involves motion, and are an essential part of any aircraft. But of course, the IMUs that are found in an aircraft are much more accurate than the MPU-6050. Some IMUs can cost as much as $100,000 for military grade. The more expensive IMUs fundamentally work much differently than the more affordable ones. The MPU-6050 is based on MEMS technology, which are essentially tiny mechanical devices that are built inside a microchip. More advanced IMUs are based on quartz/MEMS technology and utilize a piezoelectric quartz material to improve performance. But the most accurate and most expensive IMUs are typically based on fiber optic and ring laser technologies. The details of how these different technologies work is outside the scope of this video, but I just wanted to give a little insight into how advanced some of these sensors can be. But from a software and coding perspective, there isn't too much of a difference between them, and they all provide the same type of data. So learning how to use the MPU-6050 is a great place to start. As you can imagine, learning how to fully utilize linear acceleration and angular velocity data for something like an aircraft isn't something you can learn overnight, and involves a solid understanding of physics, mechanics, and advanced math such as calculus, which is outside the scope of this video, but this is something I'll probably get into in future videos. The focus today is learning how to grab the data into a Python program and doing a simple example. But it's probably still a good idea to have at least a basic understanding of what this data means. So I'll go ahead and give a quick intro right now. Let's start with linear acceleration. Now there's different ways to express motion. In addition to acceleration, there's also velocity and position or distance. And it turns out, if you know one of these, then you can calculate the others. But we also need to keep track of other variables such as time. Let's think of a car driving on the freeway to help illustrate this. When you push down the gas pedal, the car accelerates, or in other words, its velocity increases. Now let's say the car reaches 60 miles per hour and it stays at this constant velocity. Since the velocity is no longer increasing and is now staying constant, the acceleration becomes zero. Now, if we stay at this constant velocity for a set amount of time, let's say for 1 hour, we can calculate the distance traveled. Traveling at 60 miles per hour for 1 hour means we've traveled 60 miles. But what if the velocity wasn't constant and the car was speeding up and slowing down during this time? This is where calculus comes in. If we calculate the integral of an acceleration equation, we will end up with an equation for its velocity. And if we take another integral, then we can get position or distance. We can also go backwards by doing derivatives instead of integrals. So if we were to take the derivative of a distance equation, we would end up with the velocity. And if we take another derivative, then we'll be given the acceleration. Now the gyroscope is similar as the accelerometer, except we're now looking at rotational velocity. Instead of using meters or miles as distance, we're now using degrees or radians to describe how much an object has rotated around its center. An object in 3D space can rotate on its x, y, or z axis, or any combination. These axes are also referred to as the yaw, pitch, and roll in an aircraft. Now, since the gyro is measuring velocity instead of acceleration, that means if we take an integral of the gyro data at a specific time frame, we end up with the total degrees rotated in that time frame. And if we take the derivative of the gyro data, we'll end up with the acceleration. So hopefully now you're starting to get a basic understanding of how we can describe and predict any type of movement of an object by using an accelerometer and gyroscope, and by properly applying some mathematical equations to that data. So now let's move on to a simple example using the MPU-6050. Since this device communicates over the I2C protocol, the first thing we'll need to do is enable the I2C bus on the Raspberry Pi. So for the dietpi operating system, first enter sudo dietpi-config, and then navigate to advanced options. Now toggle the I2C state option from off to on. You can also change the I2C frequency from 100 kHz to 400 kHz for faster transmission speed and faster polling rate. But this isn't necessary, and you can leave it at the default speed if you'd like. Now push the escape key and exit out of the configuration, and you'll be told to reboot the Pi to apply the changes. This process is very similar if you're using the official Raspberry Pi OS, but instead of entering sudo dietpi-config, you'll enter sudo raspi-config. Next, you'll need to install the Python 3-smbus package. But if you're running DietPi, this actually isn't necessary since the previous step should have automatically installed it. Now let's install the Python library for the MPU-6050 using pip. Simply copy and paste this command here. Now we'll need to give our user permission to access the I2C bus. So copy and paste this command here, then be sure to reboot the Pi before continuing. Now, connecting the MPU-6050 to the Pi is extremely easy. Even though this is a 3.3 volt device, it also has an onboard regulator, so it's safe to connect the VCC pin to either 5 volts or 3.3 volts on the Pi. Now connect the ground pin to ground, connect the SCL pin to pin 5, and connect the SDA pin to pin 3. Normally, the SCL and SDA pins each require a pull-up resistor like you see here when connecting devices to the I2C bus. But it turns out this sensor already has these pull-up resistors built in, so we don't need to worry about that. Also, you might have noticed I soldered a 100 nanofarad capacitor on the power and ground pins here to help with filtering. But this isn't necessary, and is only useful if you're using extremely long wires. So unless you're using wires that are more than 1 or 2 meters long, I wouldn't worry about this. And finally, you can see I have the AD0 pin tied to ground, but this isn't necessary either. By default, the sensor's I2C address will be hex 68, but if you tie AD0 to the VCC pin, then you can change the address to hex 69. This is useful if you want to use 2 of these sensors in a single project, which is what I previously did. One sensor had the AD0 pin connected to VCC, and this one I have the AD0 pin connected to ground, which is actually kinda redundant since that's the default address either way. But anyway, you can just ignore the AD0 pin for this example since we're only using a single IMU. Now let's move on to the code. Let's start with this code I found on GitHub, which will grab all the data and print it onto the terminal once every second. So let's go over it. First, we import the MPU-6050 library, and then we create a new object for it on this line. You'll want to leave it as the default address unless you connected the AD0 pin to VCC like I just explained a minute ago. Now this function's job is to read in all the data. This line reads the accelerometer data, this line reads the gyro data, and this line reads the temperature data. Now let's go to the main loop. The first thing it does is call that function, which returns all the data and assigns each set of data to a different variable. Next, the program prints out each data set. Then it will sleep for 1 second and then repeat the whole process again, and will continue doing this until you close the program. Now before we run the code, I should mention that it's best to perform calibration first, since these budget IMUs aren't very accurate, and they can greatly benefit from calibration. There are different methods to do the calibration, and some are more advanced than others, but the simplest method is to make sure the sensor is flat and still, take some readings of the data, then set these readings as an offset to all the subsequent data that you'll actually use for your program. But I'll be skipping calibration today, and we'll do that in a later video where we actually implement the sensor in a project. So now let's run the code. I'll create a new file and name it mpu.py. Then I'll copy and paste the code from GitHub, save the file, and then head over to the terminal to run it. And as you can see, it's printing out the X, Y, and Z axis data for both the accelerometer and the gyro. So I'll first hold the sensor completely flat like this, and then pause the video here so we can make sense of this data. You'll notice the x and y axis in the accelerometer is close to 0, but the z-axis has a value that hovers roughly around 9.8. The units of this value are in meters per second squared, which is directly related to the unit of force. This reading of roughly 9.8 comes from the force that pulls objects down towards the ground, commonly referred to as gravity. Now, if we look at the gyro data, we'll notice the values are all close to 0, which makes sense since I'm not rotating the sensor. These values are in the units of degrees per second, or angular velocity. The reason why none of these values are perfectly 0 is partly because it's difficult to hold the sensor absolutely still, but also, like I said earlier, these are cheap IMUs, so they're not very accurate, and running a calibration first would help a lot here. But now let's continue and start moving the sensor and see how it reacts. I'll rotate the sensor like this, and then pause the video again. When I rotated it, you'll notice the y-axis of the gyroscope spiked up, and then right after that, we can see the acceleration moved from the z-axis over to the x-axis, which makes sense because now this side of the sensor is facing down towards the ground instead of the bottom of the sensor like it was before. And then when I rotated the sensor again to return to its original position, we can see there was a negative rotation on the gyro's y-axis, and the acceleration shifted back to the z-axis like it was originally. Now let's continue, and this time I'll rotate the sensor in this direction. Again, we can see the gyroscope spiked again, but this time the rotation was on the x-axis instead of the y-axis, since I'm rotating it onto a different side this time. And as expected, we can also see the acceleration has shifted again, but this time it's on the y-axis instead, which makes sense since that's the side facing down at this moment. Now let's flip the sensor completely upside down. You'll notice the z acceleration flips from positive to negative, since we're still on the same axis when I flip it upside down, but now it's in the opposite direction. So hopefully now you're starting to get the picture of what all this data means. Like I mentioned before, it would take a number of videos to fully explain how to use this data in real applications, but for today, let's just do one more simple example. Let's modify the program so that our LED turns on only when the IMU is being held upside down. So the first thing we'll need to do is figure out how to grab only the z-axis data for the accelerometer. It would be helpful to know what type of data structure this accelerometer data variable is. So let's do a print function and then call the type function on this variable. I'll also comment out the other print functions so that they don't clutter the screen. Now I'll run the program, and as we can see, it's giving us class dict, which means the data type of this variable is a dictionary. If you're familiar with Python dictionaries, then you'll know that you can grab a specific value by referencing its key. When we printed out the values earlier, we were given the keys, which are x, y, and z. So all we need to do is reference the variable with one of these keys, and we'll be given that specific value. So here's the code I came up with. First, import the gpiozero library to control the LEDs. Then, assign the LED to whichever pin is physically connected to your LED. Next, create an if statement that checks the accelerometer z-axis data. Since we're expecting this value to be around -9 or -10 when the IMU is upside down, I decided to play it safe by checking to see if this value is at least -8, just in case the reading is slightly off. When this if statement is true, then the LED turns on, and if it's not true, then the LED turns off. I also decreased the sleep time down to 0.1 second for faster reaction time. So now let's run the code. And as you can see, the LED only turns on when I flip the sensor upside down, and it turns off when I move it back to its upright position. Also, reaction time is extremely quick without any lag. And now I'll move the sensor around in various positions to show that it doesn't react to any other position. It only reacts when it's being held upside down, so it's working just as expected. Now, before we wrap up today's video, I wanted to quickly point out how adding additional sensors to the I2C bus is really easy. Since we already enabled I2C in the settings and installed the SM bus package, all you need to do is connect your new devices to the SDA and SCL pins. Then, install the appropriate library for that device. So, for example, if you wanted to add the VL53L0X laser distance sensor I mentioned earlier, simply enter this model name in Google, followed by Python. Then go to the library's GitHub page here. Scroll down to the installation section and copy and paste the Python 3 command to install the library with pip. Then go up and click the Python folder and check out the example code here to see a simple example of how to use the sensor, which can then be adapted into your own program and applications. This process will more or less be the same for any other sensor, as you should be able to find existing libraries for any sensor that's on the market. So that wraps up today's video. Hopefully now you have a decent understanding of how you can connect sensors to the Raspberry Pi and other SBCs and use them with your own Python programs. If you have any thoughts or questions, feel free to drop a comment and be sure to like and subscribe if you haven't already. In future videos, I'll be using sensors like these for practical applications and projects, so stay tuned for that. As always, thanks for watching and I'll see you next time.